Welcome to the video on maximums, minimums, optimization, and points of inflection. So first we'll talk about local maximums and minimums. So a local maximum or minimum would be in a function like this. Your absolute minimum would be negative infinity and your absolute maximum would be positive infinity. But you have a local maximum here because there's a point here that's higher than all of the points around it. And then a local minimum down here because there's a point that's lower than all of the points around it. So if the first derivative of a function changes signs, there's a local maximum or minimum. So if your derivative is positive, that means your function is increasing. So here, your derivative would be positive. And then when it starts going down again, it's going to switch to be negative. So that would mean you have a local maximum because your function's gone from going up to going down. So there's going to be a peak where it's the maximum. And then if your function goes from negative to positive for your derivative, then you're going to have a local minimum because your function's switched from going down to up and you'll have a minimum in between. The second derivative can also tell you if you have a maximum or minimum because it tells you the concavity of the function. So if the derivative is greater than 0, it's positive, so it's concave up, so you have a minimum. If it's less than 0, it's concave down, so you have a maximum. So with that knowledge, you can do optimization problems. In many cases, people need to find the maximums or minimums for profit, area, volume, or something else, and that's when you would use optimization. So using derivatives, you can find maximums and minimums to figure out where things are optimized. So we have 8 steps for how you would do that. First, you would draw a labeled diagram so that you can figure out what you're trying to solve for. Then you would write an equation for what's being optimized. So if you're trying to maximize your area, you would write your equation for area. Next, you would write the equation for the constraints on the variables. So if your length, for example, had to be twice your width, then that would be one of those equations. And in step 4, you would reduce the main equation to one variable. So if area is length times width, and we know that our length is 2 times our width, we could plug in 2w for length to get that area equals 2w times w, which is 2w squared. So then this would become the main equation with one variable. Then you would find the derivative of that equation and find critical numbers where the derivative is 0 or undefined, and you would also check the endpoints of the domain. So here our derivative would be 4w, and that equals 0 if w equals 0. So we could draw a line for our derivative, a prime. We have a 0 when our width is 0. So if a prime is less than 0, if we plugged in a negative number, we would get a negative value for our derivative. And then if we plugged in a positive number, we'd get a positive value for our derivative. So our slope is going down till 0, and then it's going to go up. So a critical point would be when w equals 0. And then endpoints would be if you have a restriction on your domain. For example, your width has to be greater than 0 for finding the area of something, and then you could have a restriction saying that it needed to be less than 10, for example. So then you would test both endpoints as well. So in step 7, you use your first or second derivative to test and find the maximums or minimums. So with your first derivative, it's like we showed here, where you can find where it's negative and positive to figure out where your minimums and maximums are, and then you can test your endpoints to see if those are either lower than your minimum if you're looking for the absolute minimum, or greater than your maximum if you're looking for your maximum. And then you could also take your second derivative. So in this case, it would just be 4. So your second derivative is always positive, which means it's concave up, and that's how you would know you have a minimum. And then your final step would be to answer the question. So in this case where we're talking about area, you could say the dimensions where the area is maximized is whatever for length and whatever for width. And we'll do practice with this in one of our IB practice questions. So next we have our points of inflection. So a point of inflection is where your second derivative equals 0 and it's changing from being positive to negative or vice versa. So negative to positive, which means you have a concavity change. So it's changing from being concave up to concave down or concave down to concave up. And just because your second derivative is 0 does not mean there's an inflection point at y equals x. So for this example, it says find the inflection point or points on the function y equals 3x cubed. So our first derivative, dy dx, is going to be 3 times 3, which is 9x, and then we lower the degree to squared. Then our d squared y dx squared, our second derivative, equals the derivative of that. 2 times 9 is 18, and then we have x to the first power. So our second derivative equals 0 if 18x equals 0. So if x equals 0. So we'll draw a line for our second derivative, f double prime, and we'll put a point at 0, and we want to test to the left of that and to the right of that. So if we plug in something less than 0 into our second derivative, so if we plug in -1, for example, 18 times -1 is negative 18. So our second derivative is negative when it's less than 0. And if we plugged in something greater than 0, like 1, we would get a positive number. So our point of inflection is where our second derivative equals 0, and it's switching from negative to positive, or positive to negative. So we know that there's an inflection point when x equals 0. So on your original function, your 3x cubed, you could plug in 0 to find the actual point where the inflection is, and that would be 3 times 0 cubed, which is 0. So there's an inflection point when x equals 0 at 0, 0. So here we have our first IB practice question where the calculator is allowed. It says a toy company's cost is given by the function c of x equals negative 0.0001x cubed minus 0.02x squared plus 15x plus 565, where x represents the number of toys and 0 is less than or equal to x is less than or equal to 165. The marginal cost, additional cost per unit, is the derivative of the cost function. How many toys to the nearest toy should the company make to minimize marginal cost? So our first step is to draw a labeled diagram. With this one, we wouldn't really need to draw a diagram because we don't have any box or volume, surface area, anything like that. So we can go to step 2, where it says write an equation for what is being optimized. So we're trying to optimize the marginal cost, which is the derivative of our cost function. So our cost function is negative 0.0001x cubed minus 0.02x squared plus 15x plus 565. So the function we're optimizing is the derivative of that. So 3 times negative 0.0001 is negative 0.0003, then it's x squared, minus 0.04x plus 15. So this is the function that we're going to optimize. Step 3 says write the equations for constraints on the variables. We don't have any equations other than that 0 is less than or equal to x is less than or equal to 165. So we have boundaries there. Step 4 says reduce the main equation to one variable, which it's already one variable. So then we can go to step 5, which says find the derivative of the main equation. So we need to find the derivative of our marginal cost. So that'll be our second derivative, which equals negative 0.0006x minus 0.04. Step 6 says find the critical numbers where the derivative is 0 or undefined and the endpoints. So our endpoints are going to be where x is 0 and where x is 165. And then we want to find where our derivative of the function. So the original function that we're referring to is this one. So we'll look where our second derivative, c double prime of x, equals 0. So 0 equals negative 0.0006x minus 0.04. We'll add 0.04 to both sides. So we get 0.04 equals negative 0.0006x. And then we'll divide both sides by negative 0.0006. So that gives us that x equals negative 200 over 3, which is approximately 66.67. So if we were to draw that on our line, it would be all the way down here. So it's outside of the boundaries. So we know that our answer can't be negative 66.67. So it's going to have to be one of these values here, 0 or 165. So if we plug in a value between those, like 1 for example, then we'd get c double prime of 1 equals negative 0.0006 times 1 minus 0.04, which equals negative 0.0406, which is a negative number. So we know the slope is negative, meaning that our marginal cost will be minimized at 165. Because if the slope is negative, it'll be higher at 0 than it is at 165. So in order to minimize marginal cost, the company should make $165 toys. So your marginal cost for 165 toys would be C prime of 165, which is approximately $0.2325 per additional toy. Dollars per toy. This is just some additional information. All you have to do is get to this point on the question. So now we have our second IB practice question. It says James is making an open top box with a square base for his school project. It has to have a total volume of 460 cubic centimeters. The side of the box is made from cardboard and only costs 5 cents per square centimeter. The base is made of wood and costs 20 cents per square centimeter. What should the dimensions of the box be in order to minimize the total cost? So step 1 is drawing a labeled diagram. So we have an open box. So if we lay it down flat, we have our base, which is a square. So we'll call our side lengths x. And then you have each of the sides that go out like this, because then they would fold together to form a box. So you'll have your height of your box, which we'll label h. So step 2 is write an equation for what's being optimized. And this says minimize the total cost. So we're going to write an equation for our total cost. So our cost is going to equal the amount it costs for the base. So our area of our base is x times x, which is x squared. And that's going to be multiplied by the cost per square centimeter for the base. So times 20 cents. Plus, we'll have the cost for each of the sides. So each side will be h times x, and there's 4 of them. So 4xh times the price for the sides, which would be $0.05 per square centimeter. So 0.05. So our cost equals 0.2x squared plus 0.2xh. So now we have our cost as a function of x and h. Step 3 says write equations for constraints on variables. So it says there has to be a total volume of 460 cubic centimeters. So our volume equals our base times our height. So our base is x squared and our height is h. And our volume has to equal 460. So x squared times h equals 460. And if we wanted to solve for h, we could divide both sides by x squared to find that h equals 460 over x squared. We also know that x has to be greater than 0 and h has to be greater than 0 because you can't have a negative distance. So now that we've written the constraints, our fourth step is to reduce the main equation to one variable. So we're going to take this and plug it in for h so that our cost is a function of x. So c equals 0.2 x squared plus 0.2x times h, which is 460 over x squared. We can cancel an x. Then we get that cost equals 0.2 x squared plus 0.2 times 460 is 92 divided by x, which is the same as x to the negative 1. Step 5 is finding the derivative of this equation. So our c prime will equal 0.2 times 2 is 0.4, and then x to the first power. Then we have negative 1 times 92, which is negative 92, x, and then we subtract 1 from our exponent to get negative 2. So our derivative of our cost function is c prime equals 0.4x minus 92x to the negative 2. Step 6 is to find the critical numbers where the derivative equals 0 or where it's undefined. So we want to find where 0 equals 0.4x minus 92 over x squared. If x is 0, it'll be undefined because we'll be dividing by 0. So undefined if x equals 0. Then we can add 92 over x squared to each side. So we get 92 over x squared equals 0.4x. Then we'll multiply both sides by x squared to get that 92 equals 0.4 x cubed. Then we can divide by 0.4. And we get that 230 equals x cubed. So if we take the cubed root of both sides, we get that x is approximately 6.127. So it's undefined if x equals 0, and 0 if x is approximately 6.127. So we'll go ahead and draw a line for our derivative with 0 and 6.127. If we plug in a number between 0 and 6.127, like 1, we would get c prime of 1 equals 0.4 times 1 minus 92 over 1 squared. So that's 0.4 minus 92, which equals negative 91.6. So since that's negative, our derivative is negative. And then we can try a number bigger than 6.127. We can try 7. So c prime of 7 equals 0.4 times 7 minus 92 over 7 squared, which equals 2.8 minus 92 over 49, which is approximately 0.922. So since that's positive, our derivative would be positive. So our derivative goes down and then up. So we have a minimum at 6.127, which means that our x dimension should be 6.127 centimeters. So x equals 6.127 centimeters, and h equals 460 over x squared. So 460 over 6.127 squared equals 12.254 centimeters. So our height is 12.254 centimeters. And we can double check that our volume is 460, because your volume will equal x squared, 6.127 squared, times h. And this is approximately 460. And then we can figure out our cost. because our cost equals 0.2, you can look at this equation here, times x squared, which is 6.127 squared, plus 92 times 6.127 to the negative 1. So this is approximately $22.52. So the dimensions of the box should be a base of 6.127 centimeters by 6.127 centimeters with a height of 12.254 centimeters. And then this is just some work to check your answer on your volume. And then if they asked you what the cost was, that's what you would put. So in summary, if the first derivative of the function changes signs, then there's a local maximum or minimum. If it's positive to negative, you have a local maximum. If it's negative to positive, you have a local minimum. The second derivative tells the concavity of a function and can tell you whether you have a maximum or a minimum. If the second derivative is greater than 0, then f of x is concave up, so there's a minimum. If the second derivative is less than 0, then f of x is concave down, so there's a maximum. In many cases, people need to find the maximum or minimum for profit, area, volume, or something else, and this is when you would use optimization. Using derivatives, you can find your maximums or minimums and figure out where things are optimized. And finally, a point of inflection is where your second derivative equals 0 and changes from being positive to negative or vice versa. So you have a concavity change. So it would be something like this here. That's all for this video. Thank you for watching.